Hello everybody, and welcome to the Physics Corner, a series of videos in which we show how to set up and solve introductory physics problems. I'm your host, Dr. Christopher Cirola. Today's problem involves a static equilibrium problem for a uniform door. Now, carefully, when we say static equilibrium, we mean no motion whatsoever. So, we're not talking today about a door swinging open back and forth. That's a different problem, different video perhaps. We are talking about just simply the door standing still. That's what we're talking about. So let's imagine we have a uniform door. Now, what do we mean by uniform? We mean that the density or the distribution of the mass is the same throughout the entire door. Why does that matter to state that? Because it means the very center of the door is also the location of the center of mass, which we can draw or illustrate right here, like that. And that means that if we need to worry about the weight of the door will be applied at the center of mass. So we can already go ahead and sketch that in. So there's our door with our center of mass located right there. Okay, what other facts are given to us? We're also told that the door has specific dimensions. It is 2 meters from top to bottom. So let's go ahead and write that out like that. And it is 1 meter from side to side. So again, let's distinguish this here. And notice again, as usual, we don't have to be anything like a great artist to do physics problems, but we do have to pay close attention to what we are drawing and make it fit as best we can, make it as clear as possible so that we can sketch all the things we need to sketch on it. All right. We're also told that the door has hinges. Now, we're fully aware that most doors, if you look at them carefully, have 3 hinges. There's one towards the top, one towards the bottom, and one almost exactly in the middle of the axis. For simplicity purposes, we're going to ignore the middle hinge. We could include it, but all that's going to do is make the problem much more invasive, much more difficult to solve, and it's not really going to emphasize any more physics. It'll have a lot more algebra, but it's not going to teach us any more physics as such. So, to keep things kind of lighter and doable, we're going to assume there's just 2 hinges on this particular door, knowing that in practice there's actually 3 hinges. So what that means is this: we'll put a hinge approximately here and another hinge approximately here, like that. These 2 distances in the problem are already listed as 25 centimeters or 0.25 meters, like that. Now notice we're going to the center of the hinge as well. That's what counts most, if we have to be that specific. So with these things in mind, let's start talking about the knowns and unknowns. So the mass is given as 45 kilograms. And since we usually assume gravity is 10 meters per second squared, I'm going to cut to the chase because it will be simpler for us to do this today and just simply list the weight, or mg, of the door as 450 newtons, like that. Okay, so we'll just do that. Now, there are other knowns in the problem. They're the dimensions of the door, but I'm not going to list them here simply because they will show up as we do the problem. So we're going to take our cues from the picture that we're drawing here, or pictures, plural, okay? What about the unknowns? Well, those obviously the forces acting on the door. Let's talk about that a little bit. So if we look at a picture like this, weight is already going straight down, so that hints that there's a vertical component. And doors, well, at least the door I've got drawn for you folks today, is horizontal and vertical. So let's make that our directions too. So let's do our kind of almost standard positive y going up and a positive x to the right, like that. And that will suggest some things we can do for our doors. Okay, or for our hinges. Now, for the hinges, there are 2 different hinges. And because there's 2 different hinges, I do need to label them differently. There'll be a top hinge and a bottom hinge. So there'll be a force acting at the top hinge and a force acting at the bottom hinge, like this. So one more thing about this though, as we already know, forces are vectors and therefore can be more than one-dimensional, and that will be the case here. We'll show that. So we do need to worry about forces acting on the top hinge in the horizontal and forces acting on the top hinge in the vertical. Forces acting on the bottom hinge in the horizontal, and forces acting on the bottom hinge in the vertical as well. So those are our knowns. In fact, those are the questions from the problem, right? We're trying to figure out what's happening there. So how do we go about setting this up? Okay, well, first of all, let's think about the vertical business. I think that's the easiest part to accomplish first. So if the weight of the door is pulling down, then each hinge must be holding the door's weight upwards, right? So there'll be a force we can talk about right here, and we'll call that FTY for the force from the top hinge going up, and another one here, FBY, sorry, also acting and going up like that. Now, this is the easiest one to see, and you don't really have to even do a calculation for this. As long as the hinges are equally spaced, they're doing the same effort, so to speak. There's nothing strange about the hinges otherwise, they're the same hinges. They each share half the load, and so before we even get into it, and we don't have to write an equation, we will, but we can just kind of already go ahead and assume this, that the bottom hinge and the top hinge will share the weight, and if the weight is 450, then each of them has 225 newtons, like that. Okay, so we could get a little bit more fancy and show how to solve that a little more carefully, but I have another purpose in mind for our problem here today that involves torque a little bit more carefully, and that's a little bit more important for us. So, in any case, we know that much, but that's not the full answer because the hinges must also be exerting horizontal forces. Now, at first glance, how is that possible, right? But let's take a look at this. There's a weight right here. The weight is not directly underneath either of these hinges. It's off to the side, which means if you have a force acting off to the side like that, that's a torque. And therefore, if there's torque involved, there must be a counter torque to keep the door from rotating. Therefore, we also need some horizontal forces. Now, how do we get these horizontal forces? Well, let's take a look at that with a sample model. I'll just use a sheet of cardboard. So we're using a cardboard sheet to represent our door. It's got approximately the correct relative dimensions. Notice what happens when we remove some of the hinges. So we have a top hinge and a bottom hinge, which I'm simulating with my thumbs. Now, if I remove the top hinge, notice what happens to the board or the door. It goes that way, which means that the hinge must be pulling it back this way. So the direction of force on this hinge is in this direction. On the other hand, if we keep the top hinge and remove the bottom hinge, notice what happens. The board or door wants to rotate like this, which means that this hinge here is trying to push the door that way. So the force acting from this hinge is in this direction. Okay, so when we grab the sheet of cardboard, we kind of sketch out what might happen here. So your door looks more or less like this, right? So it's hinge here, hinge there, something like that. And so here's your top hinge and your bottom hinge. What would happen if we removed, say, the top hinge? Well, as you saw in the demonstration, if the top hinge is removed, the whole door kind of rotates around the bottom hinge. Something to this effect, right? So the top hinge was over here, bottom hinge is there, and the whole door is rotated like that. Which means what? It means that the top hinge must be, at least in part, exerting a force that direction to keep the door from rotating like that, okay? So we can go ahead and put in a force up here. There is and my apologies for the same color as everybody. There is a force acting from the top hinge in the X direction, so FTX, pointing in that direction, okay? Similarly, if we remove the bottom, if we remove the bottom hinge, what will happen? Well, then again, the whole door will rotate around the top hinge, and we can sketch it like this, as we saw in the demo before. But now the bottom hinge is over here somewhere, kind of behind, unfortunately, in our picture, like that. And again, the whole thing is rotated like this, but notice what has to happen to keep that from happening. The bottom hinge has to exert a force in this direction to push the bottom of the door that direction. So the actual direction of the force from the bottom hinge is in this direction. We'll call that FBX, like that. So I have FTX, this horizontal force from the top hinge going to the left, and I have FBX, this force from the bottom hinge going to the right. Okay, so those are our forces and our pictures and the arguments for how we can talk about the directions. So we've already talked about the directions then. We have that particular part of the problem solved. Of course, what we want to do is solve for the amounts of force acting horizontally from those two hinges. We already made an argument for the vertical pieces. What about the horizontal pieces? So to remind ourselves of how all this works, we have some rules that go with our forces and now our torques. Net torque, for example, and net force in static equilibrium problems must both be equal to 0. Remember, there's no net acceleration and there's no net angular acceleration. There's no net linear acceleration, we can now call it, right? And no net angular or rotational acceleration. So the total torque, the total force, both of those acting on the door must be 0. Now, forces we've already got drawn as vector arrows and such, so we don't need to have anything else for those specifically, but we do need an equation to help us figure out what an individual torque is. Remember, an individual torque is not as simple as a force. It's not simply a push or a pull. Torque is a push or pull off axis in a particular direction, right? So we have to acknowledge that. And so an individual equation for torque is usually presented like this. You have a force that's exerted at some point. There's a distance from the axis of rotation, r, to where the force is acting, and then there's an angle between these two vectors. So that's the general equation for an individual torque. And that's what we're going to be talking about for these two hinges in a moment. Also, we'll see if we have to bring in the weight to the door itself, which probably have to, right? Think about it for a moment. One more little interesting detail I'm going to throw in there. If the angle is 0 degrees, sine of 0 is 0, there's no torque. That will come in handy. Or, conversely, also, if the angle is 180 degrees, again, sine of the angle is 0, and again, no torque. Which means what? It means if I have a force that's either pointing directly towards or directly away from the door, or excuse me, from the hinge or axis of rotation, specifically, we don't have any torque. On the other hand, if we have an angle of 90 degrees, sine of 90 degrees is 1, and then it's just the distance multiplied by the force. Now, there's an interesting trick that physics people will do with this particular situation. So if the angle is 90 degrees, then we'll often say, or write the equation like this, a little bit differently. What's this mean? It's force multiplied with something called the lever or moment arm. I'll call it lever arm here first today because I'm using an L, so lever arm. But moment arm would also fit in this particular case. And we'll show you as I draw out the picture what I mean by that particular idea, okay? So, but it's a shortcut so we don't have to do as many calculations with angles and things like that. Turns out it's actually very useful when we get to it. Okay, so what's a force equation or force equations? What are the torque equations that we can use? So force we've already got listed, or we can get started. We have a set of coordinate axes, x and y, so we can write down force equations in x and y. So the net force in the x direction is equal to what? All right, well, there's an FBX pointing to the right. There is an FTX pointing to the left. And that's it for forces in horizontal. Notice weight is perfectly vertical, and so are these other forces from the hinges. We did that on purpose, right? And because everything's standing still, that's equal to 0. Which means what? Well, it means that those two forces have to be equal to each other. That's an interesting bit of information. It's helpful, but it's not enough to solve anything, right? It just means that they're doing equal amounts of force. Okay, vertical direction, Fy net. We have the force from the top hinge, Fty. Oops, that's supposed to be an Fty. There we go. And we have a force from the bottom hinge, Fby. Now both of those are going up. And then there's the weight to the door going down. And again, because it's equilibrium, I set that equal to 0. Again, there's no acceleration. This tells us that the two hinges are both holding the door up, which, of course, we just said that. And that makes perfect sense. Now, again, I just made the argument, and I'm not going to go through the specific math you can go through to make sure that that's the case. We could do that. I'm more interested in the horizontal forces. We're going to simply make the argument here today that they have to share the load, so to speak, and so take the 450 and split it in two. There you go. Okay. Now, what about torques? What about the horizontal forces? How do we relate all those together? So, problem is that we haven't defined an axis or axes of rotation yet. This is something we have to think about, because when we did force problems, it wasn't just that we said, F equals ma and go from there. We specifically made this statement. We said, positive x goes to the right, positive y goes up. When you do rotational problems in anything but a trivial fashion, same kind of idea, you have to set up a coordinate axis, if you will. But because it's rotation works a little bit differently. So how would this possibly rotate? Now, remember again the demo we did earlier of how the door could possibly rotate along an axis. Now, that particular axis would be, for example, like this. So let's suppose we remove the top hinge, which means that the door is rotating around the bottom hinge. So that's this picture here, and there's our bottom hinge. That means the axis is actually sticking through, like this, if you will. If I can hold it that way so people can see what I'm doing. It's actually going into the paper like that, or into the door, or cardboard, okay, like that. The rotation was in that direction. So rotation is either clockwise or counterclockwise, depending. And we can define positive or negative in a moment as we feel fit to do so. But that also means we are defining rotation around this axis. We're going to call that axis B for bottom, okay? Now, by the way, we could also do an axis for the top over here and talk about rotation around the top hinge and call that axis T, if you will. But let's stick with bottom for the moment, see what happens with that, okay? So that means when we set up a torque equation, the torques will be around axis B. So let's write that out so everybody sees exactly what I'm talking about. So torque about axis B. B is the hinge. Now, again, why are we not talking about the door swinging open? Because that's not the problem. Our problem here today isn't talking about swinging the door open or closed. Our problem here today is simply asking or addressing the questions, what's keeping the door standing still in the first place? Why doesn't it just fall to the ground? That's our questions here. And we don't have to worry about the door swinging open or closed. That's a separate problem. This problem is just simply holding the door up in the first place. So that's why we're approaching it in this fashion. Okay, so torques around hinge B. What are those torques? Well, individual torque, again, is RF sine theta, or tau equals FL if we pull this particular trick. So let's take a look at the various forces and ask if they contribute torques or not. Now remember, a short version of this for torques, if a force vector is either pointing directly towards or directly away from the hinge, no torque. Also, if the force is acting at that particular point, no torque. Why? Because then R or L are both equal to 0. No distance from the point, no torque. Which is to say, by the way, as a reminder, every time we do a torque problem, we have to have a distance away from the axis of rotation. You cannot have a torque acting at that location. It doesn't exist. You can have lots of forces, but not a torque. So, which means what? It means when we look at hinge B, check it out. Force of B and Y, force of B and X, they're both acting at that point. So there'll be no torque from either of these forces right here. So when talking about the torques acting on hinge B, the forces acting at hinge B don't contribute anything. Now, that's not to say they don't contribute torque in other places. If we were to analyze the torque around hinge T up over here, that would be a question to talk about. But we're not talking about that right now. We're talking about the torque around this hinge, okay? Now, let's take a look at some of the other forces involved. Let's also cut to the chase. If you look carefully, there's a force of the hinge T, the top hinge, going in a vertical direction. Notice it's going directly away from that hinge, right? From this axis rotation. And again, that's an angle of 0 degrees. Sine of 0 degrees is 0. So here's a force acting directly away from the hinge. No torque. Again, it has nothing to do with the force. It's saying that there's no torque contributed from this force. Which leaves us with what? We've eliminated most of the forces. So do we have anything left? Of course we do. What are those forces? One of those is this force here. This is the weight. So let's sketch this out a little bit over here quickly. Do a real quick rough sketch. Again, there's our center of mass, and here is our hinge like that. And I want to show this little lever arm or moment arm trick, okay? So we could do this, right? We could say, there's a distance r from the hinge to this. Then, of course, there's the weight mg like that, right? And then you'd have to figure out what the angle is here. Now, we do have enough information, by the way, to get that task done. We could do that. But there's a quicker shortcut. Instead, let's try this trick. So again, let me re-sketch our door in very quickly, put our center of mass in and our hinge. And what I'm going to do is I'm going to drop a little straight line through the center of mass all the way down like this, and I'll draw another line going across like this from the hinge that way. And notice something that happens then. The force is acting along this line, right? So here's the force acting in this direction. Let's take this force vector and move it from here to here. So there's our mg. And then let's draw a vector L, not r this time, but L, from the hinge to that point there, like that. Notice I've got then an angle of 90 degrees, okay? So the same force, I just moved the force down. Notice that L is a different length than r was, right? And that's going to compensate for the change of angle. If we didn't use the 90-degree angle, if we used this angle instead, that would be a smaller angle. Sine would give us a smaller result, but that would be compensated by this r. So it turns out that this is a legitimate trick, which is to say the torque from the weight of the door is mgl, right? Now, one more thing. What is L in the first place? We actually have a number for that, right? Because we can go back up to our original picture of the door. Here it is. And we said the door is uniform. The center mass is at the very center of the door, which is to say that if the total width of the door is 1 meter, then of course halfway across is half a meter. So multiply that by half a meter. Okay, there we go. All right, one last bit, and this is worth mentioning because we do have to pay attention to signs. Notice again that this force from the door is going to try to make the whole door rotate clockwise. So the rotation from this torque is a clockwise torque. Now, it doesn't matter in some absolute sense whether you call clockwise or counterclockwise positive or negative, just like it didn't make us a big difference if we said going up or going down in vertical direction is positive. What I will say is that once you make your choice, like we did in the past, you have to stick with it. So if I decide to say that going clockwise, in this case, clockwise is positive, then if anything else happens that's counterclockwise, that'll be a negative torque, okay? So let's call that positive since I already have that drawn in. And so short version is this then. The contribution of torque from the weight to the door itself is simply the weight to the door multiplied by this straight line distance here, like that. Okay. All right, so if that's the case, where is there another possible torque, right? So let's sketch our door in one more time. Now, I'm doing this because I think it's a little bit easier to see what's happening if I do this rather than junk up this picture over here anymore. It's already pretty junked up, if you will. So let's do that. And in this case, I'm going to put in both of the hinges. This is my question now. So in this case, there's a force from the top hinge going to the left that we called FTX before. Give that a name. There's a distance from one hinge to the next. What is that distance? Well, the total distance was 2 meters. Here to here is a quarter of a meter, and here's another quarter. So this total distance here is half a meter. So 2 meters minus the extra half on the outsides is 1.5. So this distance is 1.5 meters, the way we've got this configured. In this particular case, notice that the angle is already a right angle, so I don't have to worry about any finessing of my formula. It's already there. And also the sense of rotation from this torque would be this way. So if I said that going clockwise is positive, counterclockwise in comparison must be negative. So subtract FTX and its distance 1.5 meters as so. Now those are the only two forces involved. Therefore, that's it for the equation. notice that we've now solved for ftx pretty quickly. Okay, so let's do that. So do our solution over here, ftx, move it to both sides, the other side. We'll have an mg. We have a 0.5 meters that's with mg. We'll have to divide by the 1.5 meters here, like that. Okay. mg was 450 newtons. If you look at this, 0.5 divided by 1.5 is 1/3. 1/3 of 450 is 150 newtons. And that's our answer, everybody. That is the force exerted by that top hinge. Now, earlier on, we showed you that the amount of force of the bottom hinge is the same as the top hinge. So that's also equal to the magnitude or amount from the bottom hinge, FBX, like that. So, kind of an interesting thing, the torque equation was actually, in a sense, even more useful than the force equation. Not because it's more fundamental or anything like that, but because it was able to incorporate some of the information we had about the door and its dimensions, and that allowed us to do some comparisons between the forces. Now, one last thing just to mention is, and that's one of those things is if you want to do this or not. If you want to go ahead and define actual specific directions for the hinges, you can always do your trig, because you now have y components for your forces, right? And now you have x components for your forces. You will notice that the top hinge will be pointing in one particular direction and the bottom hinge in another direction. They won't be identical directions overall, but that's fine. Okay. All right, and that is how we solve it. One last thing to say before we go today. Now, let's suppose if instead of using the bottom hinge, I used the top hinge. What would it look like? Well, you would then construct a torque equation about the top hinge. To give you a start on that, these two forces would not contribute to torque because they're at the hinge. This force here, which is pointing straight up towards the hinge, again, would not contribute to torque. And so the two forces you'd be using from the top hinge would be the weight of the door again and FBX. Notice how that comes out nice and neat, right? And more or less, essentially, you would end up creating an equation that looks almost identical to this and coming up again with 150 newtons and so on. But that would be good practice for everybody else to try on their own. All right. Technical support for these videos comes from Sidney Gautrow and Sophia Turner. Funding is granted to us by University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Sorolla. Thank you, everybody, for your attention, and clear skies.